Alrighty then. So if you haven't noticed in your email, I put together a 10-question quiz for Module 5 to take care of that. And that's available. What you do, just do it. There's a upload, first attempt upload. Upload it there, and I will check very often to see if there's anything there to grade, and I'll grade it and get it back to you. The first upload, just in case you start worrying about something or other, the first upload is actually worth 0 points. Now, if you do the first upload and you get 10 out of 10, well, your quiz is still going to be 10, but that particular upload is 0 points because Blackboard needs that sort of stuff. And I made the other one 10 points, and that's where your grade will go, whether you need it to use that upload or not. I can put that grade in there. So just in case you start wondering about why one's 0 points and the other one's 10 points. Okay, and you know we're looking at stuff from Chapter 5. Let's see, and I had promised to get some worked problems from section 4.5, so that's a few days ago now. I did record those finally. I just haven't been able to upload them. And I do have some other stuff from Chapter 5 that I just haven't gotten to upload yet. So that's kind of where we are. Again, an exam on beginning on Thursday, and the project stuff. I've got some stuff for you to do, but I don't want to. I don't want to have you working on 16 things at once for the class. So we've got enough to do right now instead of worrying about that. So okay. Questions on any exercises or anything like that from Chapter 5 right now? No? Okay. Well, what I thought might be a good thing to do, I could be wrong, but I think it's a good thing to do, is go to the review section of 5, because we've kind of, at least in class, we talked a bit about all these different antiderivatives and derivatives of the different types of functions and so forth. So we've got the basic theoretical concept. Okay, beyond that, it's a matter of just knowing what antiderivatives are and derivatives and so forth, and working that way. And so I thought we could look at some of the various problems at the end of the in the chapter review, where they've got lots of different things from this chapter all put together, and so I thought we could just do some problems out of there, and so I'm going to kind of jump around a bit, actually, just as I see something that looks like it could be a nice one to look at. So I'm going to do, this is number 54, and this is out of the chapter review. So this starts, I'm going to just say starts on page 393. Now, 54 itself, I think, is on 394 here. But they would like the definite integral from 0 to 2 of e to the 2x over e to the 2x plus 1 dx. And, you know, as I look at that, well, yeah, probably I need to use substitution to get this done. If they were reversed, well, I guess I'd still need to use some substitution, but if they were reversed, I'd have a single expression under the, a single term in the denominator, and I could actually divide up the numerator into the two pieces by the addition. But since I have a sum in the denominator, I'm stuck. You know, so I'm just stuck with this. Well, it's in the denominator, and so, well, I guess maybe that's e to the 2x plus 1 inside the 1 over x function. Okay, the reciprocal function. And so I'm going to try that. I'm going to try u equals e to the 2x plus 1, and then du would be e to the 2x, because the derivative of e to the 2x is e to the 2x, but then times the derivative of 2x. Okay, so we end up with 2e to the 2x, okay, because of that derivative of 2x there, and then plus 0. Derivative of constant is 0. And so then, with our filling out our differential there, dx. And this is almost perfect, right? I've got e to the 2x dx here. I just don't have that 2. And so I'll write this as 1/2 the integral from 0 to 2 of 2e to the 2x over e to the 2x plus 1 dx, like that. And so now I've got my du right there. There's u, and I've got the 1/2 out in front. Now, I still need to take care of my limits of integration. Now, technically, you don't have to. I mean, you could leave these as 0 and 2. Now, if you did, you should start writing x equals, so that, you know, because if I don't see anything here, I assume that these values go with that variable x. But when I make my substitution, I'm going to be using the variable u. Well, so if you didn't change these, you better keep writing, you know, saying x equals. Otherwise, it's wrong. Okay, so, but I think overall the easiest thing to do usually is to go ahead and make the substitution for the bounds as well. So I have u equals e to the 2x plus 1, and x is 0, so u of 0 is e to the 2 times 0 plus 1. That's e to the 0, which is 1, plus 1 is 2. And u to the 2, so that's e to the 2 times 2 plus 1. And so that's e to the 4 plus 1. And it's just not going to get any nicer than that. And so we can now change this overall to 1/2, and my bounds now go from 2 to e to the 4 plus 1. And I have du over u. And so at this point, I just have a power rule. I've got u to the negative 1 there. So I'll put it down here. So I have 1/2 the integral from 2 to e to the 4 plus 1 u to the negative 1 du. And so finally, I can write that as 1/2 and do my antiderivative. So that's u to the, right, that's u to the negative 1. So when you first look at it, you might go, oh, that's u to the 0, right? Oh, no. I really probably shouldn't have written it that way. It's a habit. trying to put things as negative exponents. But that's u to the negative 1. That's not a power rule. Right? When I was looking at it, I just went, oh yeah, you know, power rule, always power rule. But no, this is the one case, right, where it's not a power rule. That is natural logarithm. And so the antiderivative here is natural log. Now, it should be the absolute value of u. And in this case, this is one of those cases where if you don't write that to begin with, you're actually not wrong. I mean, you might be wrong, right? If I really were to ask you about it, you might go, oh, yeah, I forgot I'm supposed to have an absolute value. But notice, you know, 2 is greater than 0, and e to the 4th plus 1 is greater than 0. So I don't need the absolute value on there. I know I have positive arguments to put in. So, you know, you could put that, but if in this particular case with a definite integral, if you were to leave that off with these positive bounds here, you're actually not wrong. And so we get natural log, 1/2, and then our natural log. Now I'm going to drop the absolute values. E to the 4 plus 1, and then minus natural log of 2. And, you know, this is good. That's a perfectly good answer. You're not going to simplify it much more than this. The best I can do is, since there's a minus here, I could combine these two logarithms as the logarithm of e to the 4 plus 1 all divided by 2 inside the logarithm. And if I really wanted to, then with the 1/2, I could take that inside to the power 1/2 or make a square root sign. Right? So I can do more with this if I want. You know, so I am perfectly happy with an answer like that. Okay, but you could, if you were really trying to make it look fancy, do the natural logarithm of the square root of e to the 4 plus 1 divided by 2, like that. And you might put some parentheses around it like that. Okay, but like I say, I'm quite happy with that answer. And to some extent, you know, when I see that answer, I can see exactly what you did, so I like that answer. Again, you know, for the test, you know, remember that you have technology, but it's going to say you need to justify your answer. So, you know, for a problem like this, yeah, I need to see this stuff. Okay, I can't just, you know, it can't be you start with this and then you give me some decimal for the answer. Okay, that's a typing exercise. And there are times when that's the right thing to do, but for an exam where you're trying to show you understand these integration rules and so forth, that is not the right time to use it. So, okay. All right, any questions about 54 there? And this is, you know, to some extent, I would say this is about as hard a problem as one gets, in that, you know, there's a substitution, there's e to the x stuff going on. You know, now, any particular problem, you know, so from a structure point of view, that's probably as hard as it gets, but it could be you have no issues with something like e to the x, but oh, you give you a sine function or something, and then you have trouble. You know, everybody's different. Okay, so here's some stuff, you know, just to kind of show us that we can do this kind of thing. 93, you know, it's all about just realizing what the big picture is. So I've got the antiderivative, so this is an indefinite integral, antiderivative of the hyperbolic secant squared over the hyperbolic tangent, like that, dx. Okay, so we have these two functions that I never deal with hyperbolic tangents and hyperbolic secants and all that, you know. But I turned back a few pages, and 5.8 is hyperbolic functions, and on page 385, it has a bunch of derivatives and antiderivatives. And I see that the derivative of the hyperbolic tangent is indeed the secant squared, hyperbolic secant squared. Okay, that is the derivative of that function down there. Oh, well, that's all I needed, right? That's all I needed from this, because now I'll say, well, let u equal the hyperbolic tangent, and then du, according to page 385, I think I said 385, is just the hyperbolic secant squared, and then dx. And so, making those substitutions, this is just an antiderivative of 1 over u du. And that I can do. So, you know, I really don't have to know even what the heck a hyperbolic tangent is. Okay? And I don't need to know a hyperbolic secant. Now, it's good to have some notion, and if I know my trig derivatives and antiderivatives quite well, as I look at this, I'm not real surprised by this relationship. Okay, because I know the derivative of the tangent is the secant squared. And so, oh, well, that's nice that, you know, with the hyperbolic trig functions it works the same way. That's wonderful. So now that I have this, okay, the antiderivative 1 over u is just the natural log of the absolute value of u plus an arbitrary constant. And so, in this case, you darn well better have an absolute value on there, okay? Because it's an antiderivative. I don't know what I'm going to put in there. Maybe I will use negative numbers or something. And then I need my arbitrary constant. And I just need to remember to substitute this stuff back in. So there's the hyperbolic tangent of x, like that, and plus c. Okay, so, you know, I can be given some functions I've never really dealt with, but if I can just go look up what their derivatives and antiderivatives are, you know, as long as it's not too bad a problem, I can probably work it out. And of course, the things I'm looking for, you know, a lot of these are from book problems, right? Is that, well, they've done a lot in this section with the natural log function, and so I should be looking for 1 over stuff. But typically, when I do see 1 over something, or 1 over something squared, or the 1 over the square root of something, usually whatever that is in there, that's what I try to do for my substitution. Doesn't always work, but you know, as you get in, you know, if you take Calculus 2, you start learning all these other techniques, and so not everything's a substitution, because not everything came from a chain rule. Some things came from the product rule or something like that. Well, you know, when you're in Calculus 2, you can you learn some techniques, not so much to undo the product rule, like this truly undoes the chain rule, right? It kind of works backwards through the chain rule. When you do something called integration by parts, well, you can kind of think of it like undoing the product rule, but that's not exactly what it's doing. But it's using the product rule to help you do an antiderivative. Okay. Questions on 93? Anything? No. Okay. Let's see. Well, we've got some. Oh, yeah, here's a nice one. Number 19. So this is a definite integral from 1 to 4 of 2x plus 1 over 2x dx. And here, you might, and actually this might work eventually, but you end up kind of doing the same thing you have to here anyway. But here, I might look at this and I might think right off, oh, well, let u equal 2x. Because it's on the bottom and, it seems like maybe what I ought to do. Yeah, actually, if you do that, eventually you'll get to something that you can find the antiderivative of and go from there. However, you end up having to do the same thing, basically the same procedure I'm going to do right now, which is I'm just going to divide the 2x into both of those, right? I'm just going to separate it. So this is equal to the antiderivative, or well, actually the definite integral from 1 to 4 of 1 plus 1 over 2x dx. I just separated the numerator over the over the 2x. And so 2x over 2x is 1, and I'm left with 1 over 2x. Another way you could think of it is I just divided this into that. Not lots of people do polynomial division anymore, it seems like. But yeah, if I had a 2x plus 3 on the bottom here, I would probably still do something very similar. I would just divide it in there. But so I get this, and this, again, I can handle this. Right? I have my antiderivatives. So the antiderivative of 1 is just x, and the antiderivative of 1 over 2x, well, I'm going to just leave the 1/2 all by itself, and then I've got 1 over x. So I have 1/2 natural log of, again, here I don't really need the absolute values. I'm just doing that to remind you that the general antiderivative has absolute values there. So we get that from 1 to 4, and I plug in 4 first, so I have 4 plus 1/2 natural log of 4. Don't need the absolute values at that point. And then that's minus 1 plus 1/2 the natural log of 1. Now, natural log of 1 is 0. So I just get a minus 1 there. So I have a 4 and a minus 1. So I get a 3. And plus, now here, again, if you left this as 1/2 natural log of 4, I'm happy. Okay, that is perfectly fine. But remember logarithm rules, I can bring that 1/2 up here as an exponent on 4, That's 4 to the 1/2. Well, that's the square root of 4. So this is log 2. And so you could write it this way. I do expect that you know that the log of 1 is 0. I do expect you know how to subtract 1 from 4. Right? And although, in some sense, I expect that you know your logarithm rules and so forth, I'm not that worried about it. And so, you know, but if you were to look in the back of the book or something, they probably would have 3 plus the log of 2. Not 3. Probably not 3 plus 1/2 log of 4. Okay. Questions about that one? That's number 19. But this is kind of a lesson in don't forget what you already know. You know, I mean, we learn this integration by substitution and so forth, but we know about fractions and we know we can split these things up and you know, so that's just way easier than trying to worry about some sort of substitution thing. Okay, let's see. Oh yeah, how about number 50 looks slightly menacing just because it's got lots of exponentials in it. So in 50, let's see, we want the antiderivative of e to the 2x minus e to the minus 2x over e to the 2x plus e to the minus 2x dx. And, you know, like I say, at first that could look a bit menacing. But I see, you know, when I look at it, I see a fraction. And so then I focus on what's in the bottom of the fraction. And that's not always the best thing to do, but, you know, not a bad idea. So I look in the bottom and I see e to the 2x plus e to the minus 2x, and I think, well, what's its derivative? And its derivative is going to be something kind of like e to the 2x minus e to the 2x, e to the minus 2x. It's going to be something like that, but I know I've got to deal with 2's because of the chain rule. But also because of the chain rule, there's a minus there that will have to come down. And I look up there and I think, oh, well, that's kind of what I have up there. So I'm going to let u equal e to the 2x plus e to the minus 2x. And then my du, well, the derivative of e to the 2x is e to the 2x times 2. Okay, so 2e to the 2x. And then we'll have another e to the minus 2x, but when I take that derivative, I get minus 2, and so that'll be I can write it as a negative 2 like that, and dx. So I take that derivative, and I can see that substitution now. Now, what's good, if that had been like a negative 3 and that was a negative 3, I'd have been out of luck. I couldn't do this problem. Maybe you could, but I couldn't do this problem. Okay, so because the problem would be that when I did that chain rule, all right, I'd have had a negative 3 there. Well, see here, with that 2, I can multiply through the top by 2 and then, you know, multiply the bottom by 2, by doing a 1/2 out in front. But if I needed a 2 there and a 3 there, I couldn't do that. So it doesn't take much to give you something you can't do, or at least you can't do it quite as straightforwardly as we've been doing most of these problems. Okay, so, that's also something to think about is, that is that these are set up to be able to be done. Okay, they give us problems we can do, and that's just, something to remember as you do this. So here I need a 2 up there, and so if I multiply the top through by 2 and divide by 2, then I haven't changed the problem. And so now this is 1/2 the antiderivative of, I have my du on top now. Okay, there's my du, that thing times dx. So I have du, and then again over u, imagine that, it's a logarithm thing, and so we get 1/2 natural log of the absolute value of u plus c, and so that's 1/2 natural log. Now, as we look at this, e to the 2x is always positive. E to the negative 2x is always positive. And I'm adding the two together, so I never have to worry about an absolute value there. So I've got e to the 2x plus e to the minus 2x plus c. Okay. So now, actually, I don't think I see that. Oh, yes, it's right there. Number 20. I was just thinking about this problem. Number 20. Number 20 is a great problem to put on exams, that kind of thing. When you want something that, on the whole, really is supposed to be pretty easy, but it's not. I mean, when when you're faced with it the first time you see it, that kind of thing, it is not so easy. But if somebody kind of goes through it, well, it looks like, oh yeah, well, that's obvious. But the problem is, after you've done enough of these problems here, you see that x on the bottom, and you start thinking, well, okay, well, let u equal x. Wait a minute, that's silly. All I'm doing is changing the name. And so then and then you might think, well, I just can't do this because I've always substituted for what's down there. But this is a case where if I let u equal a natural log of x, then du is 1 over x dx. And there's 1 over x dx. There's du right there. And so, also taking care of the limits, so u of e, if I put e into that substitution, I get 1. And u of 1, natural log of 1 is 0. So my limits go from 0 to 1. And this becomes really a very simple problem because it's just the definite integral from 0 to 1 of u du. And so that is u squared over 2 from 0 to 1. And, well, the 0 is not going to matter. That's just going to make 0. But when I put 1 in, I just get a half. So once you realize that's the substitution you want to make, it's a piece of cake. Okay, but that's the weird thing is sometimes it's just not so obvious what you want to do for that substitution. Questions on that one? No? Okay. Let's see. There was something. Oh, yeah, okay. Some other stuff from the review. Now, these have all been integrals, definite integrals, antiderivatives. But again, another nice problem. These are great things to surprise people with. I mean, they're in homework sections and so forth, but they're great things to sort of surprise people with that they can do, but they are a bit complicated. And so, actually, I don't know that I'm going to, well, sure. We can take, we'll do number 61. It says y equals x to the 2x plus 1, and it wants the derivative. Okay, now the problem is that is neither a power function nor an exponential function. Neither one. Okay, so we're stuck. We don't have a rule for that. But again, this is where that idea that they introduced, the logarithmic differentiation, comes in, is that if I take the logarithm of y, that's the logarithm of x to the 2x plus 1, but that is just 2x plus 1 times the logarithm of x. Okay? So that, I can take the derivative of that. That's a piece of cake. Well, sort of. I mean, it's a product rule that I have to do. But I can take the derivative of that. But now, how does the derivative of this go with the derivative of y? Well, that's the implicit differentiation idea, right? See, up here, I've got an honest-to-goodness function. Y equals something. But now when I take the logarithm, I've really got an implicit situation. All right, so in order to get at y prime, I would need to maybe use implicit differentiation. And so one way to get at this is simply after I take that logarithm, to transform it into something I know how to do, is now take the derivative of both sides with respect to x. Now that's what you always do. It's just usually, right, when you see y equals, say something like y equals x squared, and you say, oh, well, dy dx is equal to 2x. Well, what did you do? Well, I took the derivative of both sides. Right? I've got dy dx on this side, and I've got the derivative on that side. And so, well, that's what we'll do with this stuff. I'm going to take the derivative of the natural log of y with respect to x, and that's going to be the same as the derivative of 2x plus 1 times natural log with respect to x. This side, I get 1 over y, because that's the derivative of natural log, 1 over something, and then times dy dx. So that's this side. And on this side, I do have that product rule. So the derivative of 2x plus 1, I've got 2 times natural log of x. And then plus my 2x plus 1 times the derivative of natural log, so 1 over x. And there we go. There's my dy dx. I just need to multiply through by y. And so I have that my dy dx, or if I want to write it as y prime, is equal to 2 times natural log of x plus, now, what I do with this thing, I could write it as 2x plus 1 over x. I could write it as 2 plus 1 over x. I guess I'll probably do the 2x plus 1 like that over x. And then that's all times y like that. Now, I wouldn't leave it like that because we know what y is, right? Y is x to the 2x plus 1. So y prime is the 2 natural log of x plus 2x plus 1 over x, and then times x to the 2x plus 1. Now, any given step here is not that difficult, but I consider these pretty darn hard problems. Even when people know pretty well that, what they're supposed to do is take the log of both sides. Okay, and that's what got us started. But, you just have to keep track of what's going on. And they're just all the, like I say, any given step is not that big a deal. This product rule, no, I can do that. Implicit differentiation, I should be able to do that. Each of those steps is not that big a deal, but these are pretty hard problems when you're faced with something like x to the x. Okay. Questions on this one? Anything here? No? Okay. Alrighty then. Let me just mention a couple things. Okay, so I sent out the quiz, and some of it just looks like exactly what you would expect. But, let's suppose I want to do this this definite integral, and what I tell you is that I know that f of 2 is equal to 6, and f of 1 is equal to 8, and that f prime of x is little f of x. What's the answer? What do I have to do? So what's this thing evaluate to? What are we using to evaluate? The silence is deafening, as they say. So how do you do a definite integral? What do you do? Just in general. How do you do a definite integral? What are the steps? Right? So, if I give you the integral from 4 to 7 of 2x dx, what's the first thing you do?
Integrate the two.
Yeah, and another way of saying that is I determine its what? Yeah, it's antiderivative. Okay, do you know this function's antiderivative? That's kind of a loaded question, but I would go with sorta. I know its name. Okay, I know the name of the antiderivative of this thing. It's right there. F of x, uppercase F of x. That's its name. Because it says so right there. That's, its derivative is that function. So this function's antiderivative is uppercase F of x. So I know that. And so, okay, I find the antiderivative. In this case, it's x squared. Then what do I do? All right, so I know this thing's antiderivative, x squared. Then what? Next step. I'm thinking you know the next step. You shouldn't be scared to talk in a class.
Do you now say that you fill in the big size if you have into the...
Yeah, so I evaluate those in the antiderivative, right? So, I do the thing where I say, oh, that's 7 squared minus 4 squared. Right? I need to evaluate those in the antiderivative. Well, so can I evaluate those? At this point, what I know is, well, by the fundamental theorem of calculus, this is f of 2 minus f of 1, just like I did there. Do I know what those values are? Sure. Right? And I just plug them in. Now, there is a little calculation to do here, because if you left it like that, well, that's not quite right. Okay, because you can do that subtraction, but you get negative 2. Right, so, this is really just an exercise getting you to think about, well, the fundamental theorem of calculus in symbols just says this. I don't need to know what these things are if you just tell me what they evaluate to. It's all about the symbols. And what's weird to me in a lot of ways, now I also suffered from the same thing, but it still seems weird to me that we have this issue, is that if, here, if instead of x squared, right, if I had done, 1 over x, and so we had our natural log of the absolute value of x there, and we had our natural log of 7 and natural log of 4. Well, when you think about it, do you actually know this any better than you know this? Right? You don't. Not really. If you've worked with natural logs a lot, you know it a little bit better. But again, let me just come up with a really complex function here where you have no idea what it evaluates to, right? So to you, it's really no different than, okay, I've got the antiderivative, I plug the number in, and somehow somebody tells me what it evaluates to. And that's all that's happening here. Somehow somebody tells you what it evaluates to. Okay? But in a lot of ways, that's what you're doing right there. Okay, because, and again, some of you, you might be okay with natural logarithms to kind of guess about what a number ought to be. But again, all I have to do is toss in like natural log of the cosine squared of, something like that. And you have no idea what it evaluates to, right? All you know is that, oh, I'm going to ask an expert. That expert is like Desmos or a spreadsheet or a handheld calculator. Don't do that though, unless it's your phone. But it's nice. I don't see too many people anymore with like TI whatevers. It's silly, that's my opinion, because you've got phones and you've got computers and laptops and all that they're way, way more powerful than that TI. But you ask that expert, sort of what does this evaluate to, and then you just put it in. Well, so there you go. Somebody told you that's how it evaluates. Now, you need to know this. If you don't know that that is the antiderivative of that little f of x, well, then it doesn't help you. I mean, it might be, but you don't know, so you can't really use it. But as long as I know, I've got this from the fundamental theorem of calculus, because somebody's told me that relationship, then, the rest, I just plug it in. There's really not much to calculate there. Okay. All righty, so that brings us to the end. I will keep working on stuff and try and get stuff uploaded, all that, and see you on Thursday.